The only new handout I have today for this class is the lab for next week. Looks like that. You copy? Got it? Okay. All right. And that will be our last lab for the semester. So you got 2, maybe 3 weeks considering the vacation. Check the syllabus, it'll give you a due date. And you can catch up if you have to. All right. So let's finish this chapter on the general concepts of bonding. I backed up a couple of slides just sort of get the ball rolling. This concept that we finished with 2 days ago had to do with determining the enthalpy of a chemical reaction. And we've done that before in previous chapters. We've used Hess's law to combine reactions and find out what the enthalpy of a target reaction is. But for this one, we used the actual energies for the bonds of all of the molecules that were entering the reaction and compared them to the bonds of the products. So we won't have to go over it in detail, but I just wanted to make that sort of a segue into the next bit of material. Here we go. Okay. So we're going to focus on covalent compounds now. Ionic compounds are really simple to deal with because they're just accumulations of cations and anions, and we can account for their bond energies with Coulomb's law. It's fairly simple. The problem arose when we tried to account for bonding that occurred between similar atoms that had similar electronegativities, not exact, but similar. And why did they bond? You know, what's the binding force there? So the short version is that a theory came out of quantum mechanics. It's called the valence bond theory. And if you do like I'm prone to do, and take the words and say, what do they mean? And that should help you inform you on the phrase itself. We're talking about bonding, of course, but we're looking at valence electrons when this bond forms. The core electrons do not enter into this theory. Now we're going to, in the next chapter, we'll look at a later version, a later theory that explains things better than this one does. But this one is still useful. Right? If it breaks down, we don't use it. And we limit its application. That's the purpose of this one. Because it's been around for longer than the next one we're going to look at in chapter 9. Okay, so what this says is that the valence electrons have these orbitals, these high probability areas, actually volumes, around the atom where they might be found. And the bonding, according to this theory, occurs when those orbitals overlap. And these are examples. Remember the dumbbell, excuse me, wrong direction, wrong button. The dumbbell shape of the p orbitals. Right? They're like that, and then they might be like this, and then they might be like that. They're in 3 dimensions. This is in one of the dimensions, p orbitals. If they overlap, then you get something that looks a little bit like this. And these two overlap, and these two overlap. Now the electrons that entered into that bond, both of them can occupy that space. Now, that's the theory. The model that goes along with it is called the localized electron model. And this sharing of electrons, according to the localized electron model, the inventive abbreviation, the sharing occurs between the atomic orbitals of the atoms. In other words, we don't create new orbitals. We just use the ones that we have. So we overlap the atomic orbitals. That may seem like a no-brainer, but when we get into chapter 9, we're gonna shift into high gear, so to speak, and create new orbitals. But now we're just using the atomic orbitals and their overlap. And this model is attributed to these folks right here. Heitler, London, of the London Dispersion Forces, and Linus Pauling. Okay, so we got a theory and we got a model to go along with it. Sometimes the models don't get their own names, but in this case, the model is so important that it does. In fact, the localized electron, the valence bond theory has a couple of models that go with it. We're going to talk about this one first, and then we're going to introduce the second one in a few minutes. Okay, so what we have to know about the bonding process is that a single bond, as we said before, is composed of 2 electrons, and they are assumed to be localized in the space between the atoms. In other words, if you get these, say if you have a, I don't know, say, let's use oxygen again. So oxygen's got 1s2, let's see, that's 8. 1s2, 2s2, 2p4. Okay. So these electrons are going to be part of the process. And if we draw the Lewis dot structure, which we've done before, haven't we? Yeah, okay. So we have these 6, 1, 2, 3, 4, 5, 6. So we have these 2 electrons here available for bonding. Right? So let's declutter. Actually, let's do it like that. So now we have this hydrogen over here with its electron, and this hydrogen over here with its electron. These electrons then, this one has a 1s orbital, and these electrons would be in the higher level, so these would be 2p electrons. That's a 1, 1s1. So what this model says is that these lone electrons pair up. So now we've got a single bond here, a single bond there, because of the overlap of their orbitals. This is an overlap of a p orbital with an s orbital. Okay. Now, once the bonds are formed, what do you have left over? Well, in the molecule, you've got these bonding pairs and these lone pairs or non-bonding pairs. We threw in definitions at the same time. So in this chapter, we're going to deal with, wait a minute. Did we do Lewis dot structures already? Or am I thinking of, no, I'm thinking of a different course.
I did it on Cengage already.
Oh, okay, okay. So that in the homework, is it?
Yeah.
Okay. So if you got into the homework, you see the Lewis dot structures, but I guess I need to go into that in detail in just a moment. Okay, so you got a taste of the future. So we're going to look at that, and the discussion here centers on the work of G.N. Lewis. And part 2 is this model here, VSEPR, and I'll define that in a second. that helps us predict the geometry of the molecule. Remember we said if you want to know a molecule's polarity, you need to know two things, right? Does it have polar bonds? Right? If it doesn't have polar bonds, then you can't have a polar molecule. But if it does have polar bonds, then you don't know if the molecule is polar until you know its geometry, what's its shape. The way that the vector addition takes all those polar bonds into account and says, what's the end result? And that's what this model does here. Okay, and this part 3 is all chapter 9. So you won't have that yet. This next exam will just be on part 1 and part 2. Okay. So Lewis structure. G. and Lewis, beginning of the 20th century, was, among other things, trying to develop a shorthand, a way of drawing his molecules so that he didn't have to draw all the proposed orbitals and all the other mess. It's a way of simplifying so that understanding can improve and subsequent construction of molecules is simpler. So the G. and Lewis developed this dot structure to account for just the valence electrons. And in fact, he focused on octets. So he's going to be looking at primarily the second and third periods. But we expand his model into the third period and beyond. But originally, it worked best for the second, third periods because that would complete a 2s, a 2s2p or a 3s3p would make 8 electrons. And those would be the valence electrons. So only the valence electrons are used in this structure. And we're headed for what we're trying to do when we put these atoms together with their dot structures is trying to create an octet around each atom, except for hydrogen, of course, that would be a duet. Okay, so there's your duet rule. Hydrogen only forms stable molecules when it shares 2 electrons, and that's as far as it can go. Right? Because it only has the 1s orbital. It can't go any further. Well, it only has 1 electron. I shouldn't say it doesn't have the one. All these atoms have those orbitals available. If you add energy and make the electron jump to higher levels, those orbitals are still available. It's just that if you only have 1 electron, then you're talking about 1s and that's it. So that's the valence. The 1s or 1 electron in the 1s from each side causes this bond to occur between the atoms. And then the octet rule, of course, fluorine's a good example where you have, well, I'm not going to draw it yet because I haven't shown you. But fluorine then would look like neon. This fluorine gets an electron in the share from that fluorine, and this fluorine gets an electron in the share from that fluorine. So this one thinks it has an octet, and this one thinks it has an octet. We didn't create any new electrons. It's just anthropomorphically speaking, they think they have an octet. Okay, that's what a single covalent bond looks like. That's 1 pair of electrons, and we denote it with this dash. And then a double bond means 2 pair or 4 electrons. So we have 4 around the carbon atom. We have 4 pairs of electrons, bonding pairs. And then a triple bond would mean 3 bonding pairs or 6 electrons. Okay, these are the steps for writing a Lewis dot structure. And I'm going to leave it up there just long enough to get it recorded, and then we're actually going to do it. I put these steps in here in case you want to go back and review. Okay. So for instance, if we have water and we have to know that the molecule exists, right? You start from a known commodity. I suppose it's possible to speculate and draw a covalent molecule and say, does it satisfy conditions that would make it possible? And you may be able to use the Lewis dot structure to say, no, that molecule won't work. It just can't work. Or you can do it this way, and you can start with a molecule that we do know exists and then draw the Lewis dot structure. And that's where we're going to start. So with water, you add up the total number of valence electrons. I guess I better do that. Unless is there an animation for that one? No, okay, so I will draw it. So if we're going to have this molecule, you count the number of valence electrons. And the best way to do that is just say, how far is it from the left? Right? Hydrogen's in that first column. So it has 1 times 2 is 2 valence electrons. And oxygen, you count over, oxygen is 6 over from the left. So it has 6 valence electrons. Okay, so we're talking about 8 valence electrons for this molecule. Now comes the tricky part. When you draw the structure, we're going to try to keep them simple in the beginning. Molecules that only have 1 central atom and everybody else is around. So in this case, we're going to put oxygen in the center. That one's an easy one actually, because hydrogen can't be in the center because it can only form 1 bond. So it has to be oxygen in the center. I'll give you some ideas about deciding which one to go in the middle. If you've got 2 or more atoms bonded and they both have the capability of multiple bonds, then you need a tiebreaker, something to tell you which one should go in the middle. In this case, oxygen's in the middle. Now, you position your other atoms around this oxygen with a single bond. Like that. So we've used up 4 electrons out of the total. We got 4 electrons left. Now what you do is you position those electrons from the outside in. Work your way toward the middle. We can't put any more around hydrogen because it's full. This 1s orbital's got 2 electrons, it thinks. So we have to go to the middle straight away. So we need 4 electrons here. 1, 2, 3, 4. Okay, so we've used up all of our valence electrons. And we see that we have 2 bonding pairs and 2 non-bonding, or 2 lone pairs in this situation. That would be a valid Lewis dot structure. Just like that. Now, that's not the way I've been drawing it. And the way I've been drawing it is as a bent molecule. And while that's true, we can't prove that yet. We need the VSEPR model to go beyond this. But now, for now, we're just drawing Lewis dot structures. So the valid Lewis dot structure has properly positioned these electrons where they need to be, in bonds and lone pairs, and we've used them all up. All the valence electrons are used. Okay. You know, that previous one wasn't right. What's it missing? The lone pairs. Yeah. So do we have a noble gas configuration here? Well, yeah. If helium thinks it has 2 electrons, then it looks like helium. And this one looks like helium. What does oxygen look like? 2, 4, 6, 8. 8 electrons. Oxygen looks like neon. So it has a noble gas electron configuration. It's isoelectronic. with neon. Okay, so let's take another example. How about PBr3? That molecule really does exist. So which one goes in the middle, right? Do we have a Br in the middle and then a P and a Br and a Br on the outside? That would be kind of unbalanced, wouldn't it? Well, there's another way to tell. Usually what happens is the lower electronegative atom goes in the center. In other words, the one that's either to the left or below the others is more metallic-like. It's not metal, but it's moving toward that direction. So phosphorus should go in the middle, right? Because it's to the left of bromine. So now we need to count our valence electrons, right? So phosphorus is 5 steps over. Right? Bromine is 7 steps over. So it's 7 times 3. And that's 21 plus 6 equals, let's say 21 plus 5 is 26. We got 26 valence electrons. Okay, so we're going to put bromine here and a bromine here and a bromine here. So that's used up 6. We got 20 electrons left. How many can go around bromine? Well, it has sufficient orbital space for 8. So ideally what you do in the beginning is you go around like this, 1 for each, and then you start adding more. So we used up 3, 6, 9. Okay, so again, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 2, 4, 6, 8, 10, 12, 16, 18, 20, 22, 24. So I use 2. Now, once you've got these filled, you move in, we got to put the 2 other electrons there. Okay, now we have 8, 8, 8, and 8. Everybody's got an octet. So that would be a valid Lewis dot structure. Oh, okay, so we finished that one off. There you go. So that's the one we just did. Now, how about this one? Hydrogen cyanide. So up to this point, we've only worked with single bonds. How do we end up with a triple bond on hydrogen cyanide? Well, there's 1 valence electron, carbon's 4 over, nitrogen's 5 over, right? So we have 10 electrons. So which one goes in the middle? Well, hydrogen can't go in the middle, but maybe nitrogen could. But look at their position. Carbon is to the left of nitrogen. So carbon should go in the middle. There we go, 2, 4. We got 6 electrons left. Okay, so we can't put any more here. We could put those 6 electrons here. 1, 2, 3, 4, 5, 6. 2, 4, 6, 8. 2, that's okay. Carbon is deficient. It only has 4. So how do you get 4 electrons around carbon without messing with your octet for nitrogen? Well, you move them over. Just go like that. Those 2 over here like that, and make a triple bond. Now this lone pair stays there, and these 2 became bonding pairs. So now we have 2 for that one, 2, 4, 6, 8, 2, 4, 6, 8. Now we've got an octet around each one. Now we're not saying that this is what happens when the molecules form. This is a procedure for for creating the Lewis dot structure. Okay. I'm going to skip these and see perhaps, let's do ammonia. The central atom is easy for this one. Hydrogen can't be a central atom, so it has to be a lone nitrogen. So nitrogen is 5 here, and 3 times 1 is 3. That's 8. 8 valence electrons. So nitrogen, hydrogen, 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 hydrogen. Says 2, 4, 6. Got 2 electrons left over. They have to go on the nitrogen. So that's the one for ammonia. How about carbon dioxide? Right. Carbon has 4, oxygen has 6 each. Yeah, 6 times 2, which would be 12 plus 4, 16. Right. So we have carbon in the middle, it's to the left of oxygen, and we create a bond for each of the oxygens. So that's 2, 4. We have 12 left over. So I know that we've got room for 2, 4, 6 and 2, 4, 6 here on the outermost. So that gets rid of all of them. So they're all used. Now we're going to do the same thing or similar process to hydrogen cyanide. We're going to take a pair from both sides. So this one's going to come over here. This one's going to come over here. Now we have octets, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. We have octets with double bonds around the carbon. And 2 lone pairs each for the oxygens. You can do the same thing with carbon tetrachloride. Right. In that case, there will be no lone pairs around carbon. All of the electrons will be used up for bonding with chlorine or lone pairs around chlorine. I'll let you do that one on your own. Now, these are well-behaved molecules, so to speak. In other words, everybody's got an octet or a duet. But there are molecules, compounds, that exist. We know they exist, but we can't get octets around them. Right? This is one exception to the rule. It's octet deficient. Right? Boron has 3 electrons, and hydrogens together have 3, so there's only 6 electrons to go around. Right? If we form the bonds, 2, 4, 6, they're all used up. But boron is deficient. What do? Nothing. It just is. That's one of the deficiencies of the Lewis dot structure model. Is, you can't make something that doesn't exist. Can't make something out of nothing. So that's a deficient molecule. Maybe that says something about its reactivity. I don't know, but it could. Then on the flip side are molecules that have more than octets. And for the same reason, you have to use up all of your valence electrons. And in this case, we have 34, and this only accounts for 1, 2, 3, 4, 8. 4 times 8 is 32. So we got 2 left over. Has to go on the central atom. And similarly with arsenic and arsenic pentabromide, when you use up all these 40, you actually have 5 bonds around arsenic, which gives it 10 electrons. Right. One thing we do notice is that when this happens, that central atom has available, easily available d orbitals. Right? So those extra electrons can be used up in overall d orbitals. I missed somebody. There's Michelle. Is Grace here? No. She's missing today. So if you look at your periodic table for sulfur, notice sulfur is in the third period. So what does N equal 3? Right? For sulfur, if N equals 3, then L can either be 0, 1, or 2. Right? There's your d orbital right there. So sulfur has easily available d orbitals to occupy those excess electrons. Similarly for arsenic. Arsenic actually is in the fourth period. So arsenic has N equals 4, L equals 0, 1, 2, 3. So there's your D. You can even go up to F. But that's how we account for violations of the octet rule. Okay, we already did the BF3. No, we didn't. We did BH3, right? Okay, BF3, we substitute fluorine in here. And if you draw the molecule, this is a valid Lewis dot structure. But notice that you got a double bond here and only single bonds there. That's another one of the failings of the Lewis dot model, the localized electron model, in fact. Is that which one of these fluorines gets the double bond? They each do, right? You could draw a Lewis dot structure that has a double bond here or a double bond there. So you have 3 possibilities. They're all valid. Right? And I'll talk about how we deal with that in a few minutes. There's an excess for phosphorus. It has available d orbitals. And there's sulfur, hexafluoride. In this case, let's see, 2, 4, 6, 8. In this case, boron does get its octet. Right, so it's not violating the rules. But phosphorus pentachloride and sulfur hexafluoride, they violate the, well, they exceed the octet. Let's put it that way. There's no violation there because it really does exist. Okay. These carbon, nitrogen, oxygen, fluorine will, in fact, I don't know of any circumstance where these would violate the octet rule. And that makes sense. Because they only have available to them 1s, 2s, and 2p. They don't have easily accessible d orbitals. Boron and beryllium very often tend to have fewer than 8 electrons around them in their complex. So what we're saying is these second row elements never exceed the octet. I don't know about never. I guess, all right, whoever put the slide together probably knows better than I do. That they never violate the octet rule. Third row elements frequently violate the octet rule or exceed the octet because they have available those d orbitals. I always try to satisfy the octet rule. If you have any electrons remaining after that octet, then they will go on the central atom. Okay, so here's another example where we have the possibility of completing the octet around nitrogen with a double bond. So we took a pair from this one and made a double bond, or a pair from that one and made a double, or a pair from this one and made a double. Okay, so these are all valid Lewis dot structures, and we can't say which one is which. We can't say which one to choose from. So we come up with a fix. Remember that when the model hiccups or fails, you have the option of amending it, right? Tweaking it. And this is our tweak for the localized electron model. It's called resonance. So what we're saying is that these are all valid structures, but the true structure is somewhere in between. They resonate back and forth. So you really can't tell. And in fact, the bond lengths, bond energies have been measured for these molecules, and all of these nitrogen oxygen bonds are equivalent in energy and bond length. So that means that nobody wins. I mean, this is not the true structure. That's not. The true structure would be something like this. Let's see, there's oxygen, oxygen, oxygen. I'm not going to draw the other electrons. So I'm just saying, instead of a double bond somewhere, it's a partial double bond, right? So that they're all equal. But this model doesn't allow us to draw that way because partially filled orbitals don't exist in this model. It either is or isn't. So we came up with resonance. Notice also, this is an ion. So when you draw the Lewis dot structure, you have to have that charge there. Otherwise, you don't have enough electrons to satisfy that model. Okay. In other words, okay, the practical application, if you drew it like that, well, like this, without the negative, it would be wrong on a test. All right. So, in the interest of time, I'm going to skip these. Sorry. Now, there's another procedure that is used, particularly in organic chemistry, to try to determine whether the Lewis dot structure that you have drawn is preferred or valid. Not just valid, but preferred. Because you can draw more than one dot structure for many molecules, but you want to know which one is more likely. And it's called the formal charge. All right, we've done oxidation states already. Oxidation states don't work as well for covalent compounds. So the formal charge was devised to help alleviate that problem. And similarly to the oxidation state, the formal charge is not a charge. It's a bookkeeping scheme, just like the oxidation state, to track the electrons and try to determine what would be the charge. Not that there is one. But what we try to do is, once we determine the formal charge for each atom in that molecule, after we draw the Lewis dot structure, and assign a formal charge for each atom, which one has the collection of formal charges that are closest to zero. So if all of them have a zero formal charge, each one, and then that's one model, and another model has a minus, a plus, -1, +1, and a 0, then all zeros would win. That would be the preferred. Okay, now we need to talk about how to do it. First of all, when you draw these structures, they can't be equivalent. If they're equivalent Lewis dot structures, like our nitrate ion in the previous slide, then you have to invoke resonance, right? You can't pick. But if they're not equivalent, then we can use formal charge to help us decide which one is preferred. The whole idea behind formal charge is that atoms and molecules try to achieve formal charge as close to zero as possible. That's a better way of saying what I said a minute ago. And if in the, that's rule number one. Rule number 2 is if you do happen to have negative formal charges of atoms around the molecule, or even the central atom, and you don't have the option for all zeros, then the negative formal charge goes on the more electronegative atoms. Right? So if it's the difference between oxygen and fluorine in an atom, and you have a negative charge that's got to go somewhere, it's going to go to the fluorine. All right, so how do we do it? Well, after you draw your Lewis dot structure, and you know all the valence electrons that are in the atom. Well, actually, that's not true. We're not talking about the whole molecule now. We're talking about individual atoms. You take the number of lone pair electrons that are assigned to that atom. Remember, this is the localized electron model. So each atom owns its electrons. So you take the number of lone pair electrons wholly assigned to an atom. So as we had carbon dioxide. If we're just doing this oxygen, those lone pairs belong to that oxygen. Okay, for the purposes of our calculation. So this would have four lone pair electrons. Then you look at the bonds. Each atom on either side only gets half of them. So we got 1, 2 electrons. Okay, we got 6 electrons that are assigned to that oxygen. On this side, same thing, 6 electrons. How many are assigned to carbon? 1, 2, 3, 4, only half of each bond. So carbon gets 4 electrons. Okay. And then you say, all right, what did they start out with as neutral atoms? How many valence electrons did oxygen have? Well, it has 6 actually. It had 6 electrons. So we say 6 minus 6 is 0. Carbon had 4. 4 minus 4 is 0. And 6 minus 6 is 0. So in this molecule, the formal charge for each of the atoms is 0. Right. So it's important to get the sign on the charge correct. Once you found out how many valence electrons are assigned to the atom in the molecule, then you subtract that from the neutral atom valence electrons. Right? It's not the other way around. You say this one has 6 valence electrons, neutral oxygen, minus how many does it have in the molecule? That gives you, in this case, it doesn't matter because they're all 0 anyway. But in some cases, you will get a difference. And I hope we have an example here coming up. Yeah, let's do this one. So this one is, how would we name that? Because that's not binary. It's not a polyatomic. Phosphorus. Yeah, I don't know. Maybe it's got a special. It's got a special trivial name. But this is the way the Lewis dot structure is drawn this way. Okay, so it looks like everybody's got an octet. That's good. So next thing we're going to do is determine what is the well, we're doing actually 2 in each step. These are the number of electrons that phosphorus has as a neutral atom. Phosphorus has 5 valence electrons. It's 5 positions over from the left. So that's 5 valence electrons. Then we find out how many electrons does it have when it's in the molecule? Well, it only has 1, 2, 3, 4. Right? Half of the bonds, 4 bonds, half of those, 4 electrons. So 5 minus 4 is plus 1. That means phosphorus has a formal charge of plus 1 in this molecule at this point. We don't have any other structures to compare. Excuse me. And we do the, oh, okay, I did animate at some point. There we go. Oxygen starts off with 6. In the molecule, it has 7. So it has a formal charge of -1. And chlorine is 6 plus 1. So it has 7. 7 minus 7 is 0. So chlorine is 0. We don't have to mess with that one. But we say, all right, is it fair to do this? Phosphorus has a +1, oxygen is -1. Let's look at where they are on the periodic table. Yeah, oxygen's above and to the right of phosphorus, so this makes sense. It's more electronegative. It has the negative formal charge, and phosphorus has the positive formal charge. All right, we didn't mention this one, but the sum of all the formal charges of the atoms in a given molecule must equal the overall charge. So if it's a neutral atom, they all have to add up to 0. And if it's an ion, it would have to add up to the charge on the ion. So here's an example of non-equivalent. If we had written carbon dioxide this way and taken 2 pair over here and put it over there, what would that do to their formal charge? Didn't give it to us. Well, we know this one's 0, 0, 0. We did that one already. This one would be oxygen has 6, so it's 1, 2, 3, 4, 5. 5 minus 6 is -1. This is still 0. And this one would be 2, 4, 6, 7. So it's 7 minus 6 is +1. Now I get that backwards somewhere. Yeah, 6 minus 7. 6 minus 7 would be -1 here, and this would be +1. +1 minus 1. But these are 0, 0, 0, so this is preferred. Right? They're all closer to 0, in fact, actually equal to 0. And this one is not. So you can throw that one out. Just a word of caution. Formal charges are estimates of charge. They're not considered actual atomic charges because these are covalent compounds. So there's no charge. It can't be a charge. Now, what it may tell us, it may inform the polarity of the molecule. Right, if you have a negative formal charge here and a positive formal charge here, and that bond should be polar toward the negative. And you have to be aware that the Lewis structures sometimes can lead to, their word is erroneous predictions. I say that just wrong predictions, not based on facts. Okay, VSEPR model. And I'm running out of time as usual. What does VSEPR stand for? V stands for valence. S for shell. E for electron. P for pair. And R for repulsion. What we're talking about here is obviously only the electrons in the valence shells, and those that are bonded from the valence shells. And we're focusing on the repulsion of those electrons because they're all negative. The lowest possible energy available to a molecule in its geometric arrangement is the one that minimizes those repulsive forces. So all of those electrons, say we had ammonia. You got electrons here, 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 and here. They're going to try to repel one another to push both the lone pairs and the bonding pairs as far away from each other as possible. So we're talking about regular geometry, right? And the regular geometry of four pairs, right? How can they point to a regular geometric structure so that they're all farthest away from each other? The tetrahedron. Now, the name is sort of created and grandfathered in as electron pair. But more properly, when we start using it, you realize that it should be a valence shell electron group repulsion, because we treat double bonds and triple bonds equally as weighty as single bonds when we talk about repulsions. And I'll show you what that means in just a second. And this is still based upon the localized electron model. Those electrons are owned by the atoms and their orbitals that are being bonded. The geometry is always relative to the central atom. So for simple molecules like ammonia, or like water, or like carbon dioxide, that's no problem. We've just got one central atom. But this model can be extended to larger molecules where you have the possibility for multiple central atoms. You can focus on each central atom independently, and it can have a different geometry around that central atom. That's true. No big surprise there. They try to maximize the distance between them. And that all refers, that's reference to the fact that the further apart like charges are, the lower the energy. And where the most stable molecules have the lower energy. All right. We can have a linear structure, right? Example there is carbon dioxide. Linear structure based upon here, right? So the bond angle, bond angle requires 3 atoms, right? Right, there's your apex, and the bond angle here is 180 degrees. That's a linear structure. Trigonal planar structure. If you have 3, like this one, boron trihydride, right? There are no lone pair electrons in there. We don't have to account for them. This would be a trigonal planar. That is the most stable, and the bond angle is 120 degrees. Tetrahedral, we showed that one referenced one. Carbon tetrachloride. Fluorine, 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 and there's one in the back of that. So we could draw a triangular structure here for the base, and then like that would give you the tetrahedral structure. And the bond angle here, you just have to memorize it, right? Bond angle there to a carbon and there is 109.5 degrees. That's really the only one you have to memorize. The rest of them are fairly obvious. There are others, and we'll talk about them in a minute, assuming I have time. Okay, how do we do it? Well, we've done part of it already. You need to draw the Lewis dot structure. But once you have the Lewis dot structure, you know which one is your central atom, and you know how many electron groups are surrounding that atom. Lone pairs are always counted separately. They're separate groups, separate pairs. Bonding pairs, depending on whether they're single, double, or triple, they're all treated the same. Let's try. Well, HCN is linear. We drew that one earlier, didn't we? So around the central atom, you got two groups around carbon, and that always is linear. pH 3. Yes, pH 3 only has that. So its bond angles are 120 degrees. Right? How do we know that? Because a complete circuit is 360 degrees, right? So 120, 120, 120, 360. Trigonal planar. Oh, no, that's not right. I'm sorry. I didn't draw the Lewis dot structure, did I? Phosphorus is 5. Plus 3 is 8 electrons. So we have 2, 4, 6, 8. There we go. That was my mistake. So we have 1, 2, 3, 4 groups, which means you could write it this way. This hydrogen is in the back. These are out here in front. Right. So we can get our triangular base, and then we got a lone pair up here. But if we draw the electronic structure, we're saying that 1, 2, 3, 4 groups means it's tetrahedral. Right? So tetrahedral would be like this. But what do we do? That's the electronic structure, is tetrahedral. How about the molecular structure? You just mask the lone pairs. What do you have left? Now you got a trigonal base pyramid. A trigonal pyramid. That's where that came from. I'm kind of jumping ahead here. This one's a seesaw, but it's going to take a little more explanation to get to that one. Has homework introduced these ideas yet?
I can't remember if it was chapter 8 or chapter 9. Though. I think the Lewis model was chapter 9 homework.
Oh, okay. Okay, so I'm going to skip these because we need a little more background. This is just a reality check. A molecule that has polar bonds will always be polar. Is that true? No, because if they're positioned, polar bonds are positioned in such a way that they cancel each other out, then the molecule is nonpolar. Okay, carbon dioxide. Well, we drew the carbon dioxide. It's a linear molecule, right? It's polar toward. I'm gonna leave out the lone pairs. It's polar this way and this way, but those bonds are equivalent. So this cancels out and makes a non-polar molecule. That's where geometry plays a part. It cancels out those dipole moments. Okay. Lone pairs make a molecule polar. Lone pairs make, not necessarily. They can add to its polarity, right? But lone pairs alone can't make a molecule polar. It depends on how they're arranged. All right, so xenon tetrafluoride. Let's see if there's anything to be gained from this one. The xenon tetrafluoride contain lone pairs. Let's see, is there all right, it doesn't give a lot of detail. Xenon tetrafluoride. Looks like I'm gonna have to stay late and talk. So if you have to go, go and I'll finish the discussion. Xenon. Oh, that's got 8, right? It's a noble gas, right? And this is 7 each times 4. So that's 28 plus 8 is 36, right? 36 electrons. Xenon obviously is in the middle. Fluorine, 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 fluorine. If we give fluorine its octets, let's see. I'm just checking. Then we know that we got 8. 1, 2, 3, 4. 4 times 8 is 32. So we have 4 electrons that need to be positioned. They have to go on the xenon, which is no problem. It's got d orbitals there. Plenty of room there. All right. So does xenon contain lone pairs? Yes, contains 2. Is the molecule polar or non-polar overall? All right, so let's take this structure and let's say I'm going to jump ahead here. How many groups do we have around xenon? We got 1, 2, 3, 4, 5, 6. We got 6 groups of electrons. All right, that means it's an octahedron, which means we go like this, square in the middle of the xenon, and then a fluorine up here. No, fluorines are here. Oops, had to write the first one. And lone pairs are like that. Okay, so this molecule has an octahedral electronic structure. If we account for all the bonds and lone pairs, it's an octahedron, right? It has 8 sides. I just draw here to here to here, have side, 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 then mirror. So we have 4 and 4 is 8. That's an octahedron. But the position of the fluorines says that the dipoles are this way. Right? But they're all equivalent. And they're pointing to the corners of a square. So they cancel each other out. That means this molecule is nonpolar. Okay. It's going to leave it up to the instructor, I guess. And it can't be polar this way because these are equivalent lone pairs. They cancel each other out. All right. So let's get some idea of how to select. First thing we have to do is electronic structure. Then we can proceed to molecular structure. And this would be the number of groups. Okay, so if we have only 2 groups, one group doesn't make any sense. One group just says it's linear because the bond is linear. So we don't need to do that one. So if you have 2 groups, like one on either side, then the electronic structure will be linear. And this has to be linear. There's no other choice. If you have 3 groups, then the electronic structure is trigonal planar. And it depends on whether you have lone pairs. If there are no lone pairs, then you still got trigonal planar molecular structure. If you have a lone pair, let's see, lone pair, then the molecule is bent, or some books call it angular. And if you have 2 lone pairs, then it's linear, and that's a no-brainer anyway. If you have four, then the electronic structure would be tetrahedral. Now we say, if there are no lone pairs, obviously it's tetrahedral. If there's one lone pair, then you get the trigonal pyramid. If there are two lone pairs, then you also get a bent molecule. You just cover up. See, if we had these were atoms and these are lone pairs, cover those up, obviously you got a bent molecule. If you have 5 groups, you have a trigonal bipyramid, bipyramidal. I think that's on the next slide. There we go. So you have 3 around the center, and then you have 2 sticking there. So it gets its name from this trigonal base, and then you have a pyramid this way and a pyramid that way. So they're like bases stuck together, a bipyramid. This is strange. It's the same if they're all occupied by atoms. If you have one lone pair, where does that lone pair occur? The lone pair usually occurs on the base of the pyramids here. So if you have a lone pair here and these are atoms, that's where you get the seesaw. If you take that and turn it this way, that becomes the legs of the seesaw, and there's the rocker. So this one's a seesaw. If you have 2 lone pairs, then you get T-shape. In other words, this would be a lone pair, this would be a lone pair, and there's your T there and there. Yeah. And the bond angles, if the bond is on the base of the pyramid, it's 120 degrees because there are only 3 of them. But if the bond is between one of these and here, that's a 90 degree. All right. Octahedral. Make some room here. So if you have 6, and this is where we're going to stop. If you have 6 groups, you have octahedral. And of course, if they're all atoms, you have octahedral. There's one lone pair. Oops. One lone pair. Where's that lone pair going to come from? Usually, the lone pair in this design comes from here, one of these. Electrons here or here. So you take the lone pair away, what do you have? You have a square pyramid. If there are 2 lone pairs, where do they come from? They come from here and here. So that gives you that xenon tetrafluoride design. So you have a square planar, they say. I don't know why they have to add that in there, but they do. If you have 3 lone pairs, now where are they going to come from? Three lone pairs usually come from the square. So you cover those up and then you have a T shape. I think that's the way it goes. And 4 lone pairs. 4 lone pairs should be linear. If linear is the case, then the lone pairs would come from here, 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 and here, and the atoms would be here. All right, now let's see if I told you wrong. There's a tetrahedron with 1 and 2 missing pairs, 2 lone pairs, 1 lone pair, 1 lone pair, 2 lone pairs. This is trigonal bipyramid. Let's see, there's your seesaw, there's your T-shape, there's a linear. So I left that one out. If you have three lone pairs in this model, then they're going to occur opposite one another, and that gives you a linear molecule. And I guess we just sort of ignore the octahedron. Maybe it's going too deep for the octahedron. It could get to be a problem. Because these models have to agree with reality. I mean, if you propose a molecular geometry and it doesn't fit the evidence, then you got to throw it away and go back and say we did something wrong. That's why with some of the models, I would think that it would be a certain way, but reality says it's another way. So I lose. Let's see. Yeah, we've got a couple of minutes. How many more slides do I have? Several. Okay, so we're going to go over time, and if you have to, depart with my best wishes. When phosphorus reacts with excess chlorine gas, the compound phosphorus pentachloride is formed. Okay. In the gaseous and liquid states, this substance consists of PCl5 molecules, but in the solid state, it consists of PCl4 plus and PCl6 minus ions. Predict the geometric structures for each of these. Okay, we can do that. Let's see. PCl5, PCl4 plus, and PCl6, PCl6 minus. Okay. So this is going to be phosphorus is five electrons in the valence shell for each one. This is 7 times 5. This is 7 times 4. This is 7 times 6. So the total here is going to be 40 electrons. This one's going to be 4 times 7 is 28. 33. Yeah. And this one's going to be 47. There we go. Okay, so let's draw this one. 1, 2, 3, 4, 5. Okay, so that's 2, 4, 6, 8, 10. Means 30 electrons. So that's 2, 4, 6 around each one. 6 times 5 is 30. That's it. We've used them all up. So what's the structure if we have 5 groups? It's a trigonal bipyramid. All right. How about this one? We've only got 4 chlorines. Right. Gotta go.
Yeah.
Okay, that's fine. So this one we've used up 8 times 4 is 32. So we got actually 1 electron. If I counted those right, 20, 33, yeah. 2, 4, 6, 8. 8 times 4 is 32. 1 electron. That's known as a free radical. When you have an unpaired electron, they're extremely reactive. See you next week.
Same.
All right, but we still count it as a group. So 1, 2, 3, 4, 5 means that the electronic structure is trigonal pyramid. But if we cover up this one in a trigonal pyramid form, like that, like this and this, where is it going to be? Well, it's probably going to be here. Right? So that means it's a seesaw. Okay, this one has 6 chlorines. Right. So let's see if we have 8 for each one. Then we say 5 times 8 is 40. That means 7 electrons left over. Right? Is that right? Oh, 6. Excuse me. 1, 2, 3, 4, 5. Oh, I do have 6. 6 times. Excuse me, I counted wrong. 6 times 8 is 48. Oops. We're using up too many electrons. All right, so one of these is going to have to be deficient. So 1, 2, 3, 4, 5, 6 means octahedral. Now, one thing I didn't do, which I should, okay, is this is a minus charge. Oh, look what I did wrong. Notice what I did? That's a plus sign. Means I have to take away let's see. 28, 3 is 33 minus 1. We're positive. That means I have to take away 1, 32. So 32 would be like this. That's tetrahedral. Okay. This one I've added 1. So this should be 48 instead of 47. Right? That's why it's important to put that charge in there. It's because I had an extra electron here and I was deficient 1 here. Right? So this one's going to be 1, 2, 3, 4, 5, 6 octahedral. Right? Trigonal bipyramid, tetrahedral, octahedral. There's the trigonal bipyramid. Right, right here. There's 32 valence electrons for the PCl4 plus. That's a tetrahedron. Okay. And the last one has 48 valence electrons. And that should be an octahedron. Okay. This is just a preface statement. Because the noble gases have filled s and p orbitals, they were assumed to be inert for real. I mean, to not form any compounds. But in the early 1960s, work was done with the larger of the noble gases, which means they have many more orbitals available, not just the s's and p's. They also have the d orbitals available. And we were able to synthesize compounds using noble gases. In fact, these 3, krypton, xenon, and radon. Now, the rest of the story is on the next slide. There's a compound that we're going to show that was created. I'm not sure which one it was. Let's see. Xenon. We already did that one, didn't we? Maybe we got these slides out of order. What would be the structure? Remember we drew it? The structure would be square planar because it has two lone pairs in an octahedral structure. Looks like this. Remember? Xenon, lone pair, and then fluorine out here. So the electronic structure is octahedral. And the bonds here are 90 degrees. And those are the only bonds that matter, because these are lone pairs. So that's square planar. Right, there it is. There's the Lewis dot structure. We have an octahedral electronic structure. Oh, this considers various possibilities. If the lone pairs are located on the square, then when we cover those up, we have a seesaw molecular structure. But if the lone pairs are opposite one another, then we have a square planar. Now, the experimental evidence says this is the structure. But we can also reason it out. We think that this is possible because what happens to electrons or their occupied space? What happens to the occupied space of electrons when they're not confined by a bond? A bond tends to focus them in the region between the atoms. If they're not confined, they tend to balloon, right? They take up more space, right? So that means they're pushing further. If they were in here at 90 degrees from one another, then they would warp this molecule. They push it apart, right? We don't see that. What we see is these bonds being equivalent in length and bond angles. So the lone pairs have to be in these apical positions. Here, here, here. So that's what I'm saying here. Lone pairs require more space. For that reason, remember ammonia. Right? Ammonia should be a trigonal pyramid with those lone pairs up there, with that lone pair up there. All right. It starts out as an electronic structure of a tetrahedron, and the bond angle in that case we would expect to be 109.5 degrees. So the bond angle here should be 109.5 degrees. But this balloon right here puts pressure on these electrons and the bonds to squeeze it down, so the bond angle is closer to 108 degrees. Okay, so square planar molecular structure is preferred for this molecule. And this refers to the polarity of the molecule. We mentioned that earlier. The bond polarity is this way, but they're all equal bonds in polarity terms, so they cancel one another out. Xenon tetrafluoride has no dipole moment, no measurable dipole moment. All right. So I was only 10 minutes over, 11 minutes over. When we meet next week, we'll do two things on Tuesday. We'll have a review for this material and then an exam on Thursday. after the review, we'll go in the lab and do the do my method. So have your notebooks prepared. I'll take a look at them on that at that time. There should be a discussion both in the method and I'm going to check to see if I've got a video discussion also that I can enable in Brightspace, because I think that will help. If you can maybe see me actually do the experiment, then you'll get a better idea of what's going on.